everyone. In this video, we are going to cover a couple more mechanisms. The first one is oxymercuration, demercuration. And then the second one is hydroboration, oxidation. So let's start with oxymercuration, demercuration. And I'm going to start by presenting a typical problem that can occur in an organic chemistry reaction. All right, so problem. Let's say that we are starting with the following alkene, and let's say that we're performing acid catalyzed hydration, which we learned about in the last video. Okay, so we know that in this process, the water molecule grabs onto a hydrogen from the acid, and we form the hydronium ion. And then our alkene acts as a nucleophile, and it will grab one of those hydrogens and deprotonate the hydronium ion. Then the shared electrons are left behind on oxygen. So what we end up forming is we get back our water molecule, and the hydrogen, remember, is going to add to the side with more hydrogens. So Markovnikov addition. So we'll end up, with a secondary carbocation here. Okay, so now water will come in and attack that positive carbon, and we'll end up forming another intermediate. And then excess water can be used to remove one of those hydrogens to create our alcohol. Let's see, so take one of those hydrogens, get rid of the positive charge on oxygen. Okay. So let's say we're performing this reaction with the hopes of producing that product. Now let's go back and look at our carbocation. Is there the potential for rearrangement there? Could we form a more stable carbocation? Yes. So what could happen, there is a hydrogen on the second to last carbon there, and we could see a 1,2 hydride shift. In fact, we would see a 1,2 hydride shift. 1,2 hydride shift. And we would end up with a, that's not what I meant to draw. Oh, I'm just going to start over with this. I'm sure you all can relate. Sometimes we end up drawing things that look a little funny. Okay, so we would end up with a tertiary carbocation after the hydrogen moves down. And then excess water, or not excess water, but our water molecule can come in and attack that carbon. So then we end up with another intermediate, and then excess water will come in and take that hydrogen, and we'll get a neutral oxygen at the end. So we do actually end up with two products in this situation. So we have an alcohol on the end of the molecule there, and then an alcohol kind of in the middle. And let's say that we really wanted to form this first alcohol that we made, but we end up with all of these contaminants from the other product. How can we isolate or just make that first alcohol without having the contamination of the other alcohol? So the question here is, how can we prevent, rearrangement? So that's where oxymercuration, demercuration comes into play. All right, so let's see how that works. Okay, so our solution is this oxymercuration, demercuration. Now, this is a really old method used by chemists, but it does involve mercury, which can be hazardous to our health. So if there's a greener way to do it or maybe different reagents to use, typically we'll go that route. But this is still a really useful reaction that we can use. So in the first step of this reaction, we're going to use something called mercuric acetate. So again, this is a hazardous chemical. And it looks like the following. So mercury is basically in the middle of, let's see, some acetates here. So what I just circled is acetate, and we can abbreviate that AC. So mercuric acetate can actually dissociate on its own to form two ions. So the electrons that are shared between mercury and one of those oxygens will break apart. Oh, and I forgot, there's a lone pair on mercury. So then what we end up with is something called a mercuric cation. So because it lost those shared electrons, it is now positively charged. And then we also have our other ion there, but the important one is the mercuric cation. And I'm going to abbreviate this HGOAC with a little positive sign on the mercury atom. All right, so that mercury cation is then going to be used in the second step, which is oxymercuration. Okay, so let's say we have our same alkene that we were using before. Okay. And again, we want the OH group to end up on the carbon there that I highlighted. So let's see how that's going to work using this mercuric cation. All right, so remember, pi bonds can act as nucleophiles. So that's going to come in and attack the positively charged mercury atom. Okay, so we're going to then form something that has a resonance structure. So I'm going to put brackets around this. Okay, so we end up with a positive charge on the highlighted carbon. And remember, mercury has a lone pair, so that lone pair can actually come in and form a bridge similar to our bromonium ion from the halogenation reaction that we talked about. So then we get this resonance structure where mercury forms a little bridge, and now it's, let's see, positively charged. And this is called a mercurinium ion. All these fun names. So instead of a bromonium ion like we get in the halogenation reaction, we're now forming a mercurinium ion. All right. Now, the hybrid structure here would have a partial positive charge on the highlighted carbon and a partial positive charge on mercury. So now in the next step, water can come in and it's going to actually attack that highlighted carbon that is partially positively charged. So another way of saying that is it attacks the more substituted carbon. And that's going to open up that ring. So then we end up with our water molecule on that highlighted carbon. All right, so it looks like we're going to end up with an alcohol group right where we wanted it. And the mercury, or the mercuric cation that bonded to the less substituted carbon, that is kind of forcing the water to come in right where we want it to. So instead of forming a secondary carbocation, we actually have this bridged structure, so there really isn't the opportunity for rearrangement here. So we're kind of blocking rearrangement from occurring. All right, so now in this next step, we need to get rid of one of those hydrogens from oxygen. And instead of drawing the water molecule coming in and taking one of those hydrogens, I'm just going to write minus H plus in brackets above the arrow. And that's just telling me that I lost one of those hydrogens. All right, so now we have mercury still attached, but we'll remove it in a second. And now we have the alcohol group right where we want it, on that highlighted carbon. Okay, so now in the very last step of this process, we're going to perform demercuration. So I'll just add a little 3 here. Demercuration. And in order to do that, we're going to use a molecule called sodium borohydride. So that's NaBH4. And let's see, I'll write that up above so you can remember. NaBH4 is sodium borohydride. Okay, and this is just going to remove the mercury acetate group, the mercuric cation. So you don't have to know the mechanism for it right now, but just know that it removes that mercury group. So then we end up with our final product, which is the one that we wanted originally. All right, so this is a really long mechanism, as you can see. But the main idea here is that the mercuric cation comes in and it forms a bridge with the carbon that we want our alcohol to bond to. So that way we're kind of blocking that position from rearrangement, which is really, really useful. But of course, there's the bad side of this, which is that mercuric acetate is a hazardous chemical. All right. So now let's talk about our next mechanism, which is hydroboration oxidation. Okay. So in hydroboration oxidation, this is going to allow us to achieve an anti-Markovnikov addition of water across a double bond. So far we've seen two ways to add water across a double bond, but we've only seen Markovnikov addition. So for instance, let's say we start with this alkene, where the double bond's on the end of the molecule. And let's say we want to form the following alcohol, plus it's enantiomer. We've seen two ways to do this. The first way involved acid catalyzed hydration. So we add a catalytic acid and water. Or to avoid rearrangement, we could use the mercury acetate, which we will abbreviate as Hg, and then OAC in parentheses, followed by a subscript 2. So that's just telling us that we have two of those groups attached to mercury, followed by water. And then in step 2, we use sodium borohydride to remove the mercury group. Now, in this particular case, we wouldn't have any rearrangement with our alkene or its carbocation, but we can still use oxymercuration, demercuration to get the same product. So even if, there isn't rearrangement occurring, we can still use those reagents to form an alcohol. But what if we want to form the anti-Markovnikov product? Markovnikov, there we go. So what if we want to take that same alkene and we want to form this alcohol where the OH group is on the very end? How do we do that? Well, we're going to use hydroboration oxidation. So the reagents for hydroboration oxidation are kind of complex. So let me just write those in here on the arrow. So we're going to start with something called borane tetrahydrofuran. So borane is BH3, and then it's bonded to something abbreviated as THF, which is our tetrahydrofuran, and I'll draw that on the next slide. We also have a second step where we use hydrogen peroxide and sodium hydroxide. Okay. So how does this work? So again, hydroboration oxidation gives us anti-Markovnikov hydration. So let's talk about what BH3THF looks like. So this is borane tetrahydrofuran. Okay. So this looks like the following. So tetrahydrofuran has an oxygen in a ring with 4 carbons, and then the borane is attached to that oxygen. So this is one of those adducts that we talked about previously, because remember, boron has an empty p orbital, and it can accept electrons. So in this case, it accepted electrons from an oxygen in this ring. So the oxygen is now positively charged, and boron is now negatively charged. Now, the reason that we use this particular reagent is because BH3 is not often found on its own. It's not often found by itself. It's often in the form of diborane, and this isn't really the correct way to draw diborane. We actually just abbreviate it as B2H6. So for this particular reaction, we really just want one borane molecule. We really don't want two. So in order to isolate borane, we add this tetrahydrofuran in there so that we can just get that single BH3. All right, now let's show what happens in hydroboration oxidation so that we can kind of see why we get the anti-Markovnikov addition. All right, so let's say that we're starting with this alkene here, and we are able to use borane from our borane tetrahydrofuran. So maybe it dissociates and comes in here. What happens is the alkene acts as a nucleophile, and remember, boron has an empty p orbital. So the alkene comes in, donates its pi electrons to the boron, and then the hydrogen is actually going to add in as well. So we kind of have a double attack going on. So what's really cool here is, let's see, the less substituted carbon ends up bonding with boron, And then the more substituted carbon ends up bonding with hydrogen. Now, this is a really long mechanism, so I'm not showing all of the components that happen here. And you don't have to know this mechanism, just know that it works really. But what we end up with is, I'm just going to draw multiple arrows here. So we end up with the boron attached to the less substituted carbon there. And then one of the hydrogens from borane ends up on the other carbon. All right. So boron attaches to least substituted carbon. Oh, that doesn't look like an N. Carbon, there we go. And this is really just due to sterics. So I'm just going to write due to sterics. So boron doesn't really attach to the more substituted carbon because there just isn't enough room. Your textbook gives a much lengthier explanation for this. So if you are more curious about that, you can go to the textbook and read it, but I don't expect you to really know this in detail. What I really care about is that you know the reagents. So if we go back, I want you to know these reagents and what they end up producing. So if you use borane tetrahydrofuran followed by hydrogen peroxide and sodium hydroxide, you get the anti-Markovnikov addition of water. All right, so I'll just write here too, long mechanism. And again, you don't have to know that mechanism. So let's look at an example of this reaction, and we'll see what kind of products we can end up with if we have stereocenters. So what happens if we can form stereoisomers? All right, so let's say that we have this starting alkene here. So we've got a cyclohexane ring with a methyl group attached. And we're going to add in our borane tetrahydrofuran followed by hydrogen peroxide and sodium hydroxide. All right, so what we'll end up with is water adding across that double bond, and the alcohol part, the OH group, is going to add to the less substituted carbon. All right, so the product looks like that. And remember, we have the alcohol group adds to the less substituted carbon, because that's the whole purpose of this reaction. Oh, less substitution, less substituted. It's hard to talk and write at the same time. Less substituted, there we go. Carbon. So again, this is an anti-Markovnikov addition. Now, again, take note, we do have some stereocenters here. So the carbon attached to the methyl group is attached to 4 different groups. There is a hydrogen bonded there as well. And then the other carbon is also attached to 4 different groups. There's a hydrogen attached somewhere there. So we could actually end up forming 4 different products, right? We have 2 stereocenters, and remember the number of stereoisomers equals 2 to the n, where n is the number of stereocenters. So we have 2 to the 2. So we could end up with a total of 4 stereoisomers. However, what's really interesting about this reaction is that we only end up forming the syn addition products. So remember, in a previous video, we talked about anti-addition products. This reaction only produces the syn addition products. So I'm just going to highlight that. That's really important. So what that means is that the hydrogen and the OH group from our water molecule, they're going to add to the same side of the ring. Okay, so we'll produce one product where both H and OH are wedges. And then we have our methyl group on the top carbon there. And that's going to be in a dash. But then we can also produce the product where hydrogen and OH are in dashes. And then the methyl group is in a wedge. And I'll just highlight those there. All right, so we only end up with 2 products for hydroboration oxidation, and those 2 products are the syn addition products. So we do not produce the anti products. Okay, so now can you figure out the relationship between these 2 products? Are they enantiomers or diastereomers? So another way to ask this without having to, do the R and S stuff, are both stereocenters, do both stereocenters change, or does one of them stay the same? So both stereocenters flipped, right? Initially we had 2 wedges and then they became 2 dashes. So would that make them enantiomers or diastereomers? Enantiomers. So we didn't even have to do the R and S stuff. All right. So again, this hydroboration oxidation allows us to add water across a double bond where the alcohol group ends up on the less substituted carbon. So we get anti-Markovnikov addition of water. Additionally, we end up only with 2 stereoisomers in this particular case, where we have stereocenters. We don't always have stereocenters in our products, but when we do, we get these syn addition products. Now, one thing to also take note of is the fact that we do have hydrogen peroxide in our set of reagents. Remember, in our hydrohalogenation reaction, we said that if you add a peroxide, you get anti-Markovnikov addition as well. So just a hint, let's see. So just a hint, if peroxides are present, you will end up getting anti-Markovnikov addition. All right, so we'll end the video there. In the next video, we're going to learn about halohydrin reactions. And we'll talk a little bit more about anti-products versus syn products. So I will see you then.